This lesson demonstrates the different components of ratios and rates. The way this lesson works is by demonstrating, first of all, how to write ratios. You'll also learn how to calculate unit rates. You will learn how to use and write ratios in table and graph form. Make sure that you write down anything in red or anything that you are otherwise instructed to, like charts and graphs, in your notes section. Also be sure to write down any blue vocabulary terms that you see in your 3-column vocabulary section. And of course, be sure to ask any questions that you might have. This video lesson is going to instruct and demonstrate how to do several different things. First, you're going to understand the concept of a ratio. You'll be able to write ratios to describe relationships between two quantities. You'll be able to calculate various unit rates. You will be able to use ratios to convert units of measurement. You'll be able to use ratios to complete tables and make graphs. You'll use ratios and rates to solve real-world problems. You will be able to understand a special ratio called pi. You'll be able to express a quantity or a ratio as a percent, which means something out of 100. Now use your Go Math or Springboard workbook to define these terms in your 3-column vocabulary section: circumference, diameter, equivalent ratios, percent, pi, ratio, unit conversion, and unit rate. Please pause the video now so that you can go and define these words in your vocabulary section. The first part of this video demonstrates and instructs what ratios are, what rates are, and how to use those to problem solve. Let's talk about what ratios are. Ratios compare two quantities, mostly two quantities. You can have ratios that compare more than two quantities, but the vast majority of ratios compare quantities, and they do this in two different ways. First, you can compare a part to a whole, or you can compare a part to part. So ratios are dealing with parts and wholes. You're either looking at how the part or how one part compares to a whole, or how one part compares to another part. There are 3 ways that you can write ratios. The first is as a fraction, where you have a quantity as the numerator and a second quantity as the denominator. The next way is to use words, where you have the ratio of one quantity to another quantity. And the third way is using a colon. All 3 of these ways are said out loud in the same way. All 3 of these we would read as A to B, A to B, and A to B. So the ratio of this to this is A to B. The ratio of this to this is A to B. And the ratio of this to this is A to B. It doesn't matter which way the ratio is written or expressed. The way we read it out loud is we use the word to in between our two quantities. The only exception to that is when you're using unit rates, and oftentimes you'll hear the word per, but it's still a ratio, and you still could use the word to. Let's look at an example on writing ratios. This example shows a part to whole. So for example, let's say that there is a class, and in this class there are 10 boys and 15 girls. What if we want to know the ratio of boys to total students? So we would ask, what is the ratio of boys to students, or boys to total students? Well, this is a part to whole ratio because boys is the part, and we're given the information that there are 10 boys. So that's the part of the part to whole ratio. Now we need to determine the whole because it's asking us to compare boys to total students. So that is the whole. This means we need to add all the parts so that we can get the whole, because the whole is the sum of its parts. Well, there are 10 boys and 15 girls, so the total, or the whole class, is made up of 25 students. Now we can write the ratio in word form or fraction form or colon form, but any of the three ways we would read it as the ratio of boys to students is 10 to 25. Now, conversely, if we were interested in the other part, what is the ratio of girls to total students, we would have the same quantity as the whole, because there would still be 25 students, but instead of 10, we would be using the number 15 because we would be comparing a different part of the whole to the whole. So it would be the ratio of girls to students would come out to be 15 to 25. Now let's look at a different type of ratio, which is part to part. Ratios can compare the parts to each other. So this is often useful if you have more than one part or more than two parts. So you could look at the different parts compared to each other. So in the same class, we have this is the same example of boys to girls, but here of the class with boys and girls. But here, instead of comparing boys to the total number of students or girls to the total number of students, we want to compare the parts to each other. So here we would say, what's the ratio of boys to girls? So now we need to determine both the parts because we're being asked to compare one part to another part. So there are still 10 boys, there are still 15 girls. We don't need to determine the whole here, or the total, because that's not what we're being asked to compare. Now we can just write the ratio. Here I've chosen to write it in fraction form. The ratio of boys to girls is 10 boys to 15 girls, or you could simply write it as the ratio of boys to girls is 10 to 15. I included the units in my fraction, but since I have the units in my statement, I don't have to include them in the fraction. Conversely, if we were asked what's the ratio of girls to boys, that would be 15 to 10. In ratios, order matters. The first quantity that's mentioned is always the first quantity in the ratio. Let's do a second example, writing different ratios. Let's say each day a factory makes 25 widgets and 15 sprockets. Now, widgets and sprockets are not a real thing. You'll often see widgets and sprockets used on different standardized tests because they aren't real, so there's no bias there when we use the words widgets and sprockets. So don't worry about what they are. They're not real things. We're just using made-up words rather than saying 25 of thing A and 15 of thing B. So each day, let's say a certain factory makes 25 widgets and 15 sprockets. If we are asked the question, what is the ratio of widgets to devices? That is a part to whole ratio. I know it's part to whole because I see the word widgets, which if I look up at my original information, widgets and sprockets, is one of the two quantities that I'm given. But in the question, the second quantity is devices. That is not an original quantity of widgets or sprockets. That means I'm looking for a part to whole ratio. So the first thing I want to do is I want to determine the part, and then I want to determine the whole. So there are 25 widgets made each day. That's my part. The whole is the sum of the parts. So there's 25 widgets and 15 sprockets. So the sum of 25 and 15 is 40. So there are a total of 40 devices made each day. Now I can write my ratio as the ratio of widgets to total devices is 25 to 40. If I had wanted, or if the question had asked me about sprockets to devices, then I would use that part compared to the whole, which would be 15 to 40. What if the question is asking me to determine the ratio of widgets to sprockets? Well, this then would be a part-to-part ratio. So I would need to determine both the parts, which is 25 widgets and 15 sprockets, and write my ratio that way, not including any whole or total numbers. So the ratio of widgets to sprockets is 25 to 15. And conversely, if I wanted to know sprockets to widgets, that would be 15 to 25. Because again, in ratios, order is important. Order matters. The first quantity in the information or in the setup of the quantities is the first quantity in the ratio itself. When you are dealing with ratios, it is extremely important to remember that ratios compare quantities. This means that your ratio must have units. If you just write 5:7, that doesn't mean anything if you don't know what you're comparing. If you write 5/7, that's just a fraction. That's 5/7. What makes it a ratio is the comparison of quantities. You have to be able to tell 5 what compared to 7 what. If you don't include units, either in the number ratio or in the statement of the ratio, it is not a ratio. You must list or include the two quantities that you are comparing. Let's talk about unit rates now. You should have defined unit rate in your vocabulary section, and so you should know that a unit rate is a special type of ratio where the second quantity or the denominator of a fraction is 1, which is where we get the term unit rate, because unit is singular. Unit rates often use the word per. If you are talking to someone or you're reading something and you see something per something, that's usually an indication of a unit rate. Here are some very common comparisons that are in the form of unit rates. So very common ratios that are in the form of unit rates. Miles per hour. When you talk about a speed as miles per hour, that's a unit rate because you are comparing the number of miles per 1 hour traveled. Also a cost per item or cost per unit. This is extremely useful in real world situations, like if you're going grocery shopping and you have two different size quantities and you're looking at which is the better buy. So let's say you have, a 10-ounce box for $5 versus a 20-ounce box for $12, you can use unit costs or cost per item or cost per ounce to figure out which is actually the cheaper or the better buy. The way to calculate a unit rate is to divide the first quantity, which is the numerator, by the second quantity, which is the denominator. That creates an equivalent fraction or an equivalent ratio where the second quantity is 1. Let's do an example of with unit rates. So we have a car, and the car drives a total of 420 miles in 6 hours. What is the unit rate of speed? And of course, we're going to assume a constant driving rate. We're going to assume that the person didn't stop to go to the bathroom or have lunch or whatever. So the question is asking us, what is the unit rate of speed if we assume a constant rate? So we need to identify what the quantities are. The first quantity we're given in this scenario is miles. The second quantity we're given is time, which is in hours. Now that we have the quantities, we want to set up the ratio that we are given. So the original ratio would be 420 miles to 6 hours. Now we can divide the first quantity by the second. So 420 divided by 6, and if you work that out, that gives us a unit rate of speed as 70 miles per 1 hour, or 70 miles per hour. Let's do another example. This one is going to talk about unit cost. So we have a crate of strawberries and it costs $5. We want to know the unit rate of that crate. So we're interested in the cost per strawberry. So how much is the cost per strawberry? And this really should say a crate is $5 for 30 strawberries, because we're looking at ratios, so order is important. So it really should say there's a $5 crate of 30 strawberries, or a crate costs $5 for 30 strawberries, rather than 30 strawberries for $5. So we're still doing the unit rate here. We still want the cost per strawberry. So we want to write the original ratio, $5 for 30 strawberries. And then we want to divide the first quantity by the second. So we want to divide 5 by 30. And really what we're doing here is we're dividing the numerator and the denominator by 30, which is how we end up with a ratio with the denominator as 1. So $5 divided by 30 is, $5 divided by 30 is 17 cents, and 30 strawberries divided by 30 is 1 strawberry. So our unit rate is 17 cents per strawberry. This next section demonstrates and instructs on how ratios and rates work with tables and graphs. We're also going to do problem solving with equivalent ratios, and we're also going to look at using ratios to convert measurements. We can use equivalent ratios to create and complete tables. Equivalent ratios are equivalent fractions, and they simplify to the same unit rate. That is how you can tell if two ratios are equivalent. They simplify to the same unit rate. So if you divide the numerator by the denominator, you wind up with the same outcome, or the same quotient. Let's do an example. So we're going to use equivalent ratios here to complete the table, and this table is a pretend recipe. You want to make sure you copy the table into your notes. So as you draw the table in your notes, you want to make sure that you are focusing on the question marks here. So we're going to fill in the slots that have the question marks, and we're going to use equivalent ratios to do this. So the quantities here are cups of flour, 4 cups of sugar. And our unit rate is 2 cups of flour for every 1 cup of sugar. So you have 2 cups of flour for 1 cup of sugar. That means all of the other ratios have to simplify to 2 cups of flour for 1 cup of sugar. Well, if I look at 4 cups of flour and 2 cups of sugar, that is equivalent, because when I divide my numerator by my denominator, 2 divided by 1 is 2, and 4 divided by 2 is 2. So those are equivalent ratios. And since I know that I need my ratio to simplify into the number 2, or 2 over 1, I can use that to figure out this question mark right here. So if I have 2 over 1, again, this is 2 cups of flour and 1 cup of sugar, and I know that my ratio for a larger recipe is going to use 6 cups of flour, then I need to know how many cups of sugar. Well, what this is really asking is, what can I divide 6 by that's going to get me the number 2? Well, that would be the number 3. So 6 divided by 3 is 2. So this is going to be 3 cups of sugar. Then I have to look at the cups of flour for the next one. I know that I'm still going to simplify to 2, because 2 divided by 1 is 2. And here I need to know what my cups of flour is going to be, but I know that I'm going to use 4 cups of sugar. So this question is really asking, what can I divide by 4 to get the number 2? Well, 8 divided by 4 is 2. So there are going to be 8 cups of flour for every 4 cups of sugar. So this is how we use equivalent ratios to complete tables. Let's do another example. Use equivalent ratios to complete this table, and here we've got a certain paint mixture. You want to make sure you copy this table into your notes, especially paying attention to the question marks. We have a new question mark here. There are 3 instead of 2. So let's take a look at the ratio we are given. You always want to look at the full ratio. Whatever full ratio you're given or complete ratio you're given, that's where you want to start. So my complete ratio here is 6 ounces of red paint for 2 ounces of blue paint. And I need to know what this unit rate is in order to figure out the other equivalent ratios. So I know that my denominator, or my second quantity, is going to need to become 1, because that is what a unit rate is. It has the second quantity as 1. So the way to do that is to divide my numerator by my denominator, or quantity 1 divided by quantity 2. 6 divided by 2. Well, 6 divided by 2 is 3. So my unit rate is 3 ounces of red paint for 1 ounce of blue paint, which is pretty cool because I have a 3 right here. So I know that 3 ounces of red paint is going to be equal to 1 ounce of blue paint. Now I can use this unit rate of 3 to 1 to fill in the other equivalent ratios, to make the other equivalent ratios. So I know that it needs to be 3 red for every 1 blue. Well, my third line tells me I'm using 9 ounces of red paint. So how many ounces of blue paint would that be? What can I divide 9 by to get 3? Or you can think of it as, what can I multiply 3 by to get 9? Well, 3 times 3 is 9, so 1 times 3 must be 3. So when you're working with equivalent ratios, it's the exact same thing as equivalent fractions. So many of you might know this sort of middle section piece to create equivalent fractions, either multiplying or dividing by a constant, and that gives you your new or equivalent fraction. And that's exactly what we're doing here. So then the final missing equivalent fraction is the last line. I know it has to simplify to the same unit rate, 3 red for 1 blue, and I know that I'm going to have 4 blue. So how many red am I going to have? Well, 1 times 4 is 4, which means 3 times 4 is going to be 12. The other way I could ask that is, what can I divide by 4 to get 3? Well, 12 divided by 4 is 3. So now I have completed my table using equivalent ratios and unit rates. Now let's look at using ratios and graphs. So if we're given a set of equivalent ratios, which will usually be given to us in a table, we can plot them as coordinates on an XY plane or on a coordinate grid. The first quantity that we're given, or the left quantity in the table, is the x coordinate. The second quantity, or the right side of the table, is the y coordinate. The x-axis, so the x coordinates, are all on the horizontal axis, which is your flat axis. And if you have trouble remembering which one that is, the way I remember it is horizon. If you look out on the horizon is flat. There's a flat line on the horizon, and so the x-axis is horizontal. And then the y-axis is vertical, which means it's going up and down. Here we have an example where we are given equivalent ratios, and we're asked to graph them as coordinates. So we have hours and we have miles, and of course you want to make sure you copy this table and this graph. So my first quantity is going to be my x quantity. So down here on my x-axis, I'm going to have hours. And so I'm going to label, this is going to be 0. We always start at 0, 0. That's the origin. 1, 2, 3, 4, 5. I don't need to go further than that because I stop at 3 in my table that I'm given. And then my right quantity, or the second quantity, is going to be my y. So that's going to be this axis, which is going to be miles. So then I'm going to label 10, 20, 30, 40. I would go by tens here. Again, I don't have to go past that because I'm only going up to 30. So I'm going to travel 1 unit on my hours, so 1 hour, and then I'm going to go up to the 10 miles on my y. So this is the coordinate 1, 10. Now I'm going to go to the 2-hour mark and then the 20-minute mark. This now is the coordinate 2, 20. A lot of people like to use the dotted lines, which is fine. And then my third coordinate, I go 3 hours, and then I go up to the 30-minute mark. So this coordinate is 3:30. Now I have graphed these ratios as coordinates. Let's do another example. Here we're given another table of ratios and we are instructed to graph them as coordinates. So let's make sure you copy the table and the graph into your notes. The graph that you're copying, it doesn't have to be perfect. You could always use some graph paper if you want to cut out a little sheet of graph paper and tape it in there. That'd be fine too, but it doesn't have to be perfect. It's not art class. So first I want to identify my x and y. My left or my first quantity is always my x. My right or my second quantity is always my y. So this on my x-axis is going to be hours studied. And so I'm going to list 0, 1, 2, 3, 4, 5, 6, and so on. I'm only going up to 3 in my table, so I'm not going to fill in the rest. And then that means my y quantity, my y-axis is going to be my quiz scores. So I have 0, and then this is 30, 60, 90. So I'm actually going to go by tens here. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. I did this so that the graph wouldn't be quite so scrunched. But your scale, which is what this is called, what you're counting by, what each unit is as long as it's consistent and as long as it makes sense for the graph, it's fine. So you could go by 30s, you could go by 10s, you could go by 20s, but I decided to go by 10s. So my first coordinate is 0, 0. So if the person studied 0 hours, they scored a 0 on the quiz. The second coordinate is 1 hour, and the score was 30. So if I go up to 30, that is coordinate number 2. Then if the person studied for 2 hours, they scored a 60. And if the person studied for 3 hours, they scored a 90. So let's think about these ratios. Would it make sense for the number, or for the coordinate 475 to be on the grid? So if the person studied for 4 hours, they made a 75. Would that make sense? No, it wouldn't make sense because it's not an equivalent ratio. We can simplify down to the unit rate and it's not the same. So it's very important that you think about equivalent ratios here so that you can have graphs that make sense and fill in the tables correctly. Now let's use ratios and rates to solve real-world problems. The most efficient way to usually do this is to use equivalent fractions. It's not the only way, but it's certainly one of the easier and more efficient ways to do so. Here's our first problem. Joe can mow 2 lawns in 1 hour. Well, if that's true, how many lawns can Joe mow in 6 hours? So the first thing we want to do is we want to write the original ratio we're given, the complete ratio. Whatever the complete ratio is, we want to write that down first. Then we want to create an equivalent ratio. And here is where you're going to be using that constant. So you're either going to multiply or divide both your quantities by the same factor. So if I need to get to 6 hours, how do I get from 1 hour to 6 hours? Well, I'm multiplying by 6. So he's working for 6 hours, so whatever he's doing for 1 hour, he's doing it 6 times. So if he mows 2 lawns in 1 hour, then in 2 hours, he's going to mow double that. In 3 hours, he's going to mow triple that. So in 6 hours, he's going to mow 6 times that. And that's where we get this constant of times 6. Therefore, if Joe can mow 2 lawns in 1 hour, then he can mow 12 lawns in 6 hours. Let's look at another problem. Becca makes $50 every 4 hours she babysits. So she wants to go on a class trip, and that will cost her $850. How many hours is she going to have to babysit in order to pay for her class trip with all babysitting money? We're not saying she's getting, birthday money or money from other places. So we're going to assume that she wants to pay for the whole trip using babysitting money. So if she makes $50 every 4 hours, how many hours is she going to have to babysit to pay for her class trip? The first thing we always want to do is write the complete ratio that we're given. The first ratio, or the original complete ratio we have, is $50 every 4 hours. Once we have that, we can use that to create an equivalent ratio. So we know that we're going from 50 to 850. So what does she need to do? How many 50s does she need to get to 850? Well, she'll need 17 50s to get to 850. So she needs 17 of her $50. Well, that means she's going to have to do 17 4-hour chunks, because every 4 hours she gets $50. So she needs 17 of this original ratio. That means she's going to have to babysit 68 hours. So if she earns $50 every 4 hours, then she'll have to babysit 68 hours to earn $850. There's a special kind of ratio we call pi, and the ancient Greeks discovered this pattern. They figured out, after lots and lots and lots of trial and error, that for any circle in the whole universe, anywhere, no matter what, dividing the circumference by the diameter will give the exact same quotient. You should have defined circumference, and you should have defined diameter. So you should know that the circumference is the measure around a circle, or the perimeter, and the diameter is the measure across the center of a circle, from one side to the other through the center. The ratio of this circumference to diameter, the special ratio, is called pi. And pi is a Greek letter, and you may have heard of it before. But that is what we use to represent this very, very special ratio of the circumference to the diameter. The ratio pi is actually an irrational number, and we'll get to irrational numbers later, but irrational numbers are numbers that are non-repeating, non-terminating decimals. So if you divide a circle's circumference by its diameter, you get this quotient, 3.14159, and it goes on and on and on and on forever. It never, ever, ever, ever stops. There are computers out there that are calculating pi to the millionth and millionth and millionth digit, because pi is irrational, so it never repeats and it never stops. Of course, we can't use that, because if it never stops, we have no ending point for pi. So what we do is we approximate it, and we usually approximate pi to 3.14 or 22 over 7. Both of these are very, very close approximations of pi. So for most purposes, they work just fine. Let's do an example of representing this very special ratio of pi. So here we want to express the ratio of pi as the ratio of this circle's circumference to its diameter. You want to make sure you copy this circle diagram. So first I want to list the information I have. I know my circumference, and we're going to use C for circumference. And that, by the way, is a very standard notation. If you are in math and you see C, it is mostly for circumference. It is 99% of the time will be for circumference. And the circumference here is 50 and 24 hundredths of a centimeter. Then I want to list the diameter that I'm given. The measure from one side of the circle to the other through the center is 16 centimeters. In order to represent or express the ratio of pi, I need to write this information as a ratio. So I'm going to write my ratio of the circumference to the diameter. And this ratio gives me pi. Let's use pi as a ratio to complete a table. And these are approximated pi values, so it's an approximated table. So make sure you copy this table into your notes. We have a circumference and we have a diameter, and we have that equals this ratio of pi. So I know that one of the approximations of pi is 22 to 7, or 22 over 7. Well, if that's true, then I can write a similar ratio. I can write an equivalent ratio of 44 to something. Well, 22, if I double that, that's 44. So then if I double 7, I get 14. 22 over 7 is equivalent to 44 over 14 because they simplify to the same unit rate. I can use this information to complete my final blank here. I've done 7 doubled, and now what have I done to get to 21? Well, that would be 7 tripled, so times 3. So here I did 22 times 2. Here I'm going to do 22 times 3. So 22, 44, 66. And so 66 to 21 is another equivalent approximation of pi. I know this because these all simplify to the same unit rate, which is pi over 1. Now we can use our knowledge of pi to determine if certain measurements could represent a circle. So let's say we're given the information that there's a circumference of 10 inches and a diameter of 4 inches. Could these be the measurements of a circle? Well, I know that the circumference of a circle compared to its diameter, or divided by its diameter, should equal pi. And I know that we approximate pi. Pi is approximately, that's the little squiggly equal sign is approximately 3.14, or pi can be approximated to, and this is another way to write approximately, 22 over 7. So if I'm given the information that the circumference is 10 inches and the diameter is 4 inches, then when I write this as a ratio, 10 inches to 4 inches, this should equal pi. Well, let's do that. What is 10 divided by 4? Ten divided by 4 is 2.5. Is 2.5 equal to our approximated value of pi? No, So this could not be a circle. Not a circle. Because the ratio of the circumference to the diameter does not give us the value of pi. We're going to continue on to unit conversions, and we use ratios and equivalent ratios to convert units. This creates a very nice if-then situation, or an if-then equation. Here's example 1. If there are 3 feet in 1 yard, how many feet are in 15 yards? With all ratio problems or unit rate problems, ratios and rates, we want to set up or write our given ratio. Whatever the complete ratio is that we are given, we set that up first. So our original ratio, our whole ratio that we're given here, quantity 1 is feet, quantity 2 is yards, and we're told there are 3 feet for every 1 yard. If that's true, which it is, it says there are 3 feet in 1 yard, then we want to use that to create an equivalent ratio. So we know we're going from 1 yard to 15 yards. Well, how do we get from 1 to 15? We multiply by 15, because remember we're using the constant factor of change, and we're going from 1 to 15, so it must be multiplying and not dividing. So we have 1 times 15 gives us 15 yards, which means that we're going to have 3 feet 15 times. And so 3 feet 15 times is 45 feet. So if there are 3 feet in 1 yard, then there are 45 feet in 15 yards. Let's do another example. There are 12 inches in 1 foot. How many feet is 72 inches? Step 1 is always to write the ratio that we are given. Our two quantities here are inches and feet. So we're going to set up our original ratio, 12 inches per foot, and we're going to use that to create an equivalent ratio. We're looking for 72 inches, so we are going from 12 inches to 72 inches. So how do I get from 12 to 72? Well, I'm going to multiply. So what am I going to multiply 12 by to get 72? Well, 12 times 6 is 72. Therefore, I need to know what 6 1 feet are. Because if I have 6 12 inches, then I need 6 1 feet. So 12 times 6 is 72. 1 times 6 is 6. If there are 12 inches in a foot, then 72 inches is 6 feet. I cannot stress enough how important your times tables are for this. It's going to save you a lot of time if you know your times tables really all the way up through 12s. You should know your times tables up through 12s. Then you should know your 15s up to about 6 or 7. And then you should really know your 20s, your 25s, all your major increments. This section is going to demonstrate and explain the idea of percent. We're also going to use equivalent ratios to find percent. We're going to solve percent problems, and we're going to express equivalent amounts as fractions, decimals, and percent. So again, percent is a special type of ratio. And it's the special type of ratio that compares two quantities, but the second quantity is always out of 100. So unit rates are a special type of ratio where the second quantity is 1. Percent is a special type of ratio where the second quantity is 100. So a percent is a ratio that communicates a quantity out of 100. How much of 100 do we have? Let's say, for example, we say 30%. So when we say 30%, what we really mean is 30 out of 100, or 30 for every 100. And we use equivalent ratios to calculate percent. So let's use equivalent ratios to calculate percent. What percent is 5 out of 25? First, like always, set up the original ratio. My first quantity is 5, my second quantity is 25. Now there's no units here. We're not doing units yet, but we will use the units in the problem solving section. So our first quantity is still 5 and our second quantity is 25. And you can think of this as parts and wholes. Our whole here is 25. That's the total that we're given. And we want the part, which is 5. So we want to know what percent this 5 is out of 25. Now we're going to create an equivalent ratio with 100 as the denominator, so our second quantity. So we're going from 25 to 100. That means we're going to be multiplying because we're getting bigger, and we have to have 4 25s. 4 25s gives us 100. So if we have 4 25s, we also need 4 5s. So we can use this information to create an equivalent ratio. 5 over 25, or 5 out of 25, is equivalent to 20 out of 100 because we have 4 of them, so it's the same unit rate. So 5 is 20% of 25 because 5 over 25 is equivalent to 20 over 100. Here's another problem solving with percent that does in fact use units. Martin went scuba diving last Saturday. His full tank began with 3,000 psi of air. During his dive, he used 75% of his air. How many psi of air did he use? First step always is to write the quantity, write the ratio that we have both quantities. Now I have 3,000 and I have 75%. 3,000 psi is a total, his full tank. But it's asking me how many psi he used. So I'm actually looking for a part here. So I can't use the 3,000 in my original ratio. Instead, I have to use the percent. I know my 75% can be written as 75 out of 100. That's what percent means. And since I now have an original ratio with part and whole, 75 out of 100, I can use that to create an equivalent ratio. I know 3,000 is my whole because, again, I have this word here, full tank. And so I know I'm going from 100, which is my whole of the percent, to 3,000. Well, how do I get from 100 to 3,000? I'm definitely multiplying, and I'm going to multiply by 30. So if I do 100 30 times, I get 3,000. If I do 75 30 times, I get 2,250. Therefore, Martin used 2,250 psi of air on his dive because 2,250 is 75% of 3,000. All rational numbers can be expressed in 3 ways: as a fraction, as a decimal, and as a percent. So we can actually write the same number, the same value, in 3 different ways. Let's take a look at whole numbers. Whole numbers can be expressed as fractions, decimals, and percents. So let's take the number 25. How can we represent or write the number 25 as a fraction, as a decimal, and as a percent? Well, to express a whole number as a fraction, which you may or may not know, you write the whole number as the numerator and the number 1 as the denominator. So you put your whole number over 1. So 25, that whole number as a fraction, is actually 25 over 1. To express a whole number as a decimal, we simply add a decimal and a 0 after the ones place. All whole numbers have decimals in them. We just don't usually write them because the decimal is an indicator that there are partial place values, the tenths, hundredths, thousandths, and whole numbers don't have any of those partial place values, so we don't need to write the decimal and the placeholders unless we are using a unit such as dollars, which has cents after the whole units place. And so that would be a situation where we would write the decimal and the zeros, but most of the time we don't. So the whole number 25 expressed as a decimal is 25 and, which is the decimal, 0 tenths. Or you could add more zeros if you wanted to. And then as a percent, to express a whole number as a percent, you multiply that number by 100, because again, percent is talking about out of 100, and you write that product with a percent sign. So 25 is actually 2,500%. Let's take a look at decimals. We want to express the decimal 34 hundredths as a fraction and a percent. In order to express a decimal as a fraction, we have to use place value. So here, the digits 3, 4 are after the decimal, and so they are going to the tenths and then the hundredths place. To write a decimal as a fraction, you simply write the digits as the numerator of the fraction, and then the place value, power of 10, as the denominator. So if we only had a decimal that went to the tenths place, it would be over 10. Here we have a decimal that goes to the hundredths place, and so this fraction is going to be over 100 because we use the place value. So 34 hundredths expressed as a fraction is 34 over 100. Of course, you always want to simplify your fractions to lowest terms unless you are instructed otherwise. So we can divide by a common factor, which here is the number 2, and we end up with a simplified fraction of 17/50ths. To express a decimal as a percent, you're going to multiply the number, the decimal, by 100. Then you're going to write the product with the percent sign. And this comes back to when we were dividing and multiplying by decimals and understanding that when we multiply by a power of 10, so 10, 100, 1000, etc., the product ends up having the same digits, but the decimal is just in a different location because we're multiplying by a place value. So here we're going to multiply 34 hundredths by 100. That gives us 34 because, again, since we have multiplied by 100, our place value is moving the decimal over 2 spots here, 1, 2, and that is where we get 34, and then we write it with the percent sign because now we're showing that it's out of 100. Let's take a look at percents now. Let's express the percent 72, so 72%, as a fraction and as a decimal. To express a percent as a fraction, all you have to do is write the number as the numerator and 100 as the denominator, and then simplify. Very easy. 72% becomes 72 over 100. Then we divide by a common factor, which here is 4, and we end up with 18/25. To express a percent as a decimal, divide the number by 100 and write the quotient without the percent sign. So this is the reverse of what we just did with the decimal. To go from a decimal to a percent, we multiply by 100. To go from a percent to a decimal, we divide by 100. So we're doing some inverse operations here. So we take 72, we divide it by 100, and we get 72 hundredths. Which makes sense because if you think about it as this fraction here, this is 72 out of 100, so it's 72 hundredths. Now let's look at fractions. Express 3/8 as a decimal and a percent. So to express a fraction as a decimal, you have to divide the numerator by the denominator, and this is where decimal division is going to become important because we're going to be using a smaller numerator than the denominator. So we are going to divide 3 by 8. And because we're dividing a larger number into a smaller number, we're going to have a decimal as an answer. So 3 divided by 8 is 375 thousandths. And that gives me my decimal. To express a fraction as a percent, you have 2 choices. If your denominator is a factor of 100, or a multiple, a factor or a multiple of 100, so 2, 4, 10, 20, 25, 50, 100, 200, 300, 400, then you can create an equivalent fraction with 100 as the denominator. If your denominator in your original fraction is not a factor or a multiple of 100, then you're going to want to divide the numerator by the denominator, which turns your fraction into a decimal, and then turn that decimal into a percent, which is multiplying by 100 and then writing the product with the percent sign. So because 8 here, 8 is not a factor of 100, we can't use equivalent fractions. We could do it, we could estimate, we could get pretty close, but that's not going to give us an exact amount. So instead, we need to divide our numerator by our denominator to turn that fraction into a decimal, and then we use the steps to turn the decimal into a percent. So we multiply the decimal by 100, which gives us 37 and 5/10, and we write that with a percent sign because we have expressed that as an amount out of 100.